So I'm Gary Greider from Los Alamos. I'm the High Performance Computing Division Leader there and have been for a really long time. Been there a really long time. So I'm going to go through another proof of what Addison said and what Dan said, and maybe take it one step further. I think both of them said, okay, you HPC crybabies, just get over it, move on, figure out how to live in the next world that you have to live in again, and get on with it. And so my first few slides will be complaining about having to do that, and then hopefully I'll get into things that I think we need to do as a community to move on to our next space, because I think we're all coming to the conclusion that we need to stop crying and move on. I cover this with eras. So I call this the pre-cloud era, and this is when times were really good in HPC and we were the big fish, and we got to say what happened when and where and how, and guide industry, and those days are long over. And then came the dark times. The cloud came upon us, and we weren't the big fish anymore, and it was cloudy. We slipped into an incredibly inefficient time, right? We lost our frequency bumps every so often, and we got cores instead, and we got no more memory bandwidth, and so we had to move into a world where we were using incredibly imbalanced systems, and they were getting more and more imbalanced, culminating with the exascale systems, which were by far the most inefficient systems ever built by mankind. And people are trying to figure out how to use them, and good for them, but that's where we landed. There was no big market to follow that really mated well with what we do. The cloud people were very, not the data centers weren't very dense. What they were doing wasn't terribly mapped to what we do, and so it was very difficult. We didn't have a fast follower to follow. We didn't have an industry to fast follow, and we were too small to make a difference ourselves. So this time of the last few years has been pretty tough on the HPC industry, because we are stuck in the middle of not mattering and following, or not being able to follow a market that really matters. And another thing that's really important in this time frame is that integrators dropped like flies. There's almost none left. Why? Because the volume is going to the cloud and the volume is going elsewhere, and the margins dropped to nothing, and so there's not a market for it anymore. It's important. And now along comes AI, and actually AI is encouraging in a way, other than using all the Earth's energy and heating the Earth a lot, and that is, it really is a little bit like us. I mean, at least it's at scale, at least they do checkpoints, at least they have to do some of the same things we do. Yes, they're doing it horribly inefficiently. Yes, they're spending more money than they need to, but at least it's dense data centers. It's very similar to what we need in many, many ways. It's unsimilar in some ways. They seem to be enthralled with dense accelerators and want to buy more dense accelerators than they know what to do with. That works for some things in HPC land, and it doesn't work very well in others. And but it's at least there's something that we could fast follow now. And yes, we're still small. And we've just gotten smaller because AI, is dwarfing everything, and cloud and AI together has dwarfed literally everything. But at least there's some promise in that there's some other community to follow or fast follow. But we have to deal with these, the outfall. We have to figure out, as was said earlier, how do we map our applications and our needs onto what we'll be able to buy, and that's important. And we'll also have to figure out, how do we deal without any integrators? There's a lot of questions, how do we manage systems when they're not, custom built for us to be easy to manage, and how do we get resource schedulers that map your way halfway in between what the cloud people use and what we need, and how do we leverage what's out there, but yet retain what we need that's somewhat unique. Another downside, is for a long time we were starting to lose our staff to all kinds of things, including cloud. We're still losing our staff, maybe as fast as we lost them before, but it doesn't seem like quite as fast. But what I've seen more recently is we're losing our best staff. Before, we were kind of losing a lot of staff. The cloud people needed to populate their ranks and cover the earth with whatever they cover the earth with. But the AI people are quite different. They're eating the absolute top. And that's a different phenomenon, and I think it's something we all have to figure out. It's part of our next life. Tough it. Let's figure out how to deal without those people. And that's an important thing, right? Because if you don't have your absolute top people, then you're going to have to leverage the community way more than you've leveraged before. You're going to have to leverage what's left. The integrators are gone. Your top people are gone. What the hell are you going to do? And so that's part of our next life, and we have to deal with it. And, in the storage systems area, which I've worked in a long, long time, it's nice to see other people actually need parallelism in the storage system, as Dan said. It's wonderful to have a market out there that's pushing this. It's unfortunate that the solutions that are emerging are mostly proprietary, and I'm a big fan of having it not that way, and you can blame luster on me, and it's good. It's out there. It's open source. It's worked for a couple of decades. Yes, it's old. Yes, there's only 2 people that answer all the questions anymore. We need to renew that somehow, right? So we need another community effort in that area, I think, to get us, to live another 20 years. And PNFS looks like potentially it's it. So let me just give you some examples of, okay, let's tough it, HPC, get on with it. What are you going to do? And most of this has to do with leveraging one another. So we walk through this valley of, cloudy whatever, and we have to emerge hand in hand as a community. Otherwise, we won't emerge. That's my message. So the first thing I want to talk about just a tiny bit, last couple of years, there's been a presentation here by Alex Lovell-Troy, who's from Los Alamos, and we've been building this thing called OpenChami. It's a open source system management thing. It's not made to just deploy systems. It's made to also manage them. So it's day 0 and day 1. It's microservices based. It's open source. We're committing new members all the time. In fact, we have 3 or 4 new members after that set of logos was snapshotted. I encourage you to join. It's one of these ways that we can, as a community, start to move towards the future of system management technology, which is microservices and containers and all the things that that are modern. And you'll have to use modern tools, or you won't be able to hire anybody that will work on it. And this is our way of trying to address that. And so I encourage people to look at this. It's pretty cool. You can install this thing, in a matter of minutes. We have systems that are being managed at LANL, production systems that go into production in the next 3 months that are going to be managed by this and deployed by this, to the chagrin of some of our so-called integrators. And some of our integrators are actually getting involved. HPE itself is looking at this and saying, well, maybe if the community does this, we can get out of this low-margin thing that we got stuck doing. And so anyway, it looks like it's got a lot of promise, and I encourage you to look at it. Another thing that we've been doing for a number of years is trying to map our applications onto what AI hardware looks like. What's AI hardware look like? It's a bunch of dense, stamps that are stamping out dense calculations as fast as they can, and they read big globs of memory, and they stamp these things out because it's all dense based. And our applications don't work that way, and I hate to say this, but they're never going to work that way. And in fact, Dan said it really, really well. Their applications don't even work that way. It's just they're using that hardware because it happens to have the most memory bandwidth known to mankind. And so anyway, our applications are never going to work that way. Theirs aren't either. They need sparse. We need sparse. And we're finally making some headway here some very interesting headway. We've been working with SK Hynix on prototyping how do you get sparse memory access to be a first-class citizen like it was in the 80s when we had really good scatter-gather hardware to leverage. And so back to the 80s, we have to go, but it's our future. And so this is how the applications work. You know, they've got this floating point array down here, and there's a couple of indices you've got to dig through to get to the floating point values you want, and you pollute your cache, and you pollute the cache lines that are moving, and all the ugly stuff that I've talked about at this event a couple of times. And what have we done about it? Well, we worked with SK Hynix to push lookups all the way out to next to the memory. So it's a logic layer that sits underneath your HBM stack, and it does lookups for you. And it parallelizes it out as wide as the number of banks you have, because that's as wide as the parallelism in a memory system. And so that's the way it works. How do you send information? How do you send requests to it? Well, you send requests to it through some stuff that we funded called indirect scatter and indirect gather, which is now in the ARM ISA. Guess what? It doesn't do anything yet, but it's in the ISA. And we have hardware now that it could potentially leverage, and we're working with a particular processor vendor to put ability for its, for it to actually pump that ISA through their ARM chip all the way out to the memory that will do the lookups for you. You still have to do work. You still have to unroll the loop, and you still have to make a list of things to scatter or to gather or to look up or to chase or pointer or whatever it is. You still have to do that work. So somebody's got to work on compilers, which we're actually funding work in that space too. But at some point, it looks like we might be able to have 4, 5, 6, 8x speedups on sparse memory scatter, gather, pointer chasing, and that kind of thing. Why is that good? Well, it's good because you don't have this GPU over here that's not working too well when it has to do sparse stuff. You've densified it. So now you can use that sparse accelerator for an HPC workload that's ugly. We found some interesting partners in this pursuit. One was Meta. Meta's recommender systems are incredibly sparse, not quite as sparse as ours, but still very sparse. And so they've been very helpful in trying to push the industry along with us. And oddly enough, we found Oracle. And Oracle has got this thing called a database. Anybody remember that? And they have these things called dense tables, and they have these things called sparse tables, and they join them, and that's called a sparse join. And guess what? It makes an indirection array just like that. And every record that they retrieve, they go through this ungodly, pointer chasing thing to get it glued together. And they are super interested in this. So we finally have some big gorillas to go to the companies that build technology and say, it's not just us. It's not just us poor HPC people that are going to have to find a new life. It's other people that need it too. And so we believe by 2028, 2029 at the latest, you will see at least one CPU vendor from a US manufacturer that has this enabled. And we also believe that there will be at least one GPU vendor that has this enabled. This is important. It's important because this is one of the last bastions of why HPC can't work all that well on dense hardware. And if we can densify all of our memory accesses, then we are way closer to being able to leverage what the industry will let us buy. This is pretty cool. Push down analytics. So the trick here is, if you're not a big community, why don't you leverage a big community? Well, there's this great, big, huge community called the Apache Analytics community, and they've been doing analytics for years, and there's tons and tons of free software out there, so much you wouldn't believe it. And so we asked the question, could you leverage that community to do our analytics? So we don't have to maintain all our own damned analytics stacks like we used to, and all our custom formats and all the stuff we've done as a community to ourselves. And so we're going to do a demo at ISC in a couple months. And it's a asteroid simulation output, uses ParaView. I think I saw ParaView as a tool that was used here a few minutes ago. Actually, that was written at Los Alamos a long, long, long time ago. sits on top of VTK, sits on top of Presto. What's Presto? Presto is this Apache query engine that spreads out and runs queries in parallel. And it pushes the queries down using this thing called substrate. And we push the query all the way down to the lowest level of a parallel file system and have the parallel file system servers actually do the analysis for us and the reductions and send the answers back up that way. It uses Arrow, which is an format, an Apache format. This is all under a PNFS umbrella, and it even uses this thing called virtual Parquet. Parquet is it's a common format for analytics. It's columnar based. It's vectors in columns. So anyway, it's pretty cool, and we worked with a bunch of companies to do this, and we think that this has got a future because we can't move data around anymore because it's getting pretty big. Ours is petabyte every dump and 10,000 dumps, and pretty soon you've got 10 exabytes, and how do you do analytics on 10 exabytes? Well, you sure as hell don't want to move it. And so you need to reduce it at the source if you can. That's what this is all about. And it's pretty interesting. And also, we need to find ways of bridging to our friends in the cloud and AI and leverage them and work with them. One of the ways is object file gateways. Dan mentioned objects, and objects, in my opinion, are kind of stupid, but they're useful for what they're useful for. It's interesting, every time I turn around, every month at least, there's an article about a new thing that tries to map objects into file. And what's fascinating about it is underneath the objects is a file. So we're mapping, and we're overmapping, and we're mapping again. Anyway, we funded, there was a popular object gateway called MinIO that mapped between file and object. They took that off the market because they weren't making any money off of it. So I said, well, crap, let's write a check to somebody that's interested in doing this. We funded this company called Versity, and they wrote this really cool object gateway. They wanted it for their own purpose because they're this archive company, and they wanted to make tape look like object, and their tape looked like file. And so they wanted it, I wanted it, so I paid them. It's open source. It's really cool. It's written in Go. It's really high performance, even though it is in Go. And the reason why is because Google works really hard on making web-oriented stuff in Go fast. And it's very high quality because it gets the hell beat out of it because Google beats the hell out of it. And so it's pretty cool, pretty nice. And it's just a gateway. So, it's got IAM for all the security parts. It's cloud. It looks like S3-ish kind of stuff, right? But under the covers, it's just a bunch of plugins. And you can put in whatever kind of storage system you want in it and whatever kind of metadata system you want in it. So anyway, I encourage you to download it, use it, contribute to it. It's another one of these community things that we have to do as a community. And another one is, how are we going to use LLMs? And of course, everybody wants to use LLMs, and everybody's using LLMs. I was talking to Dan about how we're using LLMs to try to make sure that one policy at the lab isn't negating another policy at the lab because we have too many policies.
The problem is bad data.
You got that right. And so, but one of the ways that we really like to be able to use LLMs is we have, I don't know, maybe 2 or 3 exabytes of data. And guess what? It's in files. And there's a lot of them. Trillion files, 100 billion directories, spread across a bunch of storage systems, lived for 70 years. It's been in trees. It's protected by POSIX. It's separated from one another by POSIX. So some people need to know this stuff, and some people need to know that stuff. And then some stuff can be known by everybody. So how do you build an LLM model that leverages all this, but yet honors POSIX need to know, so that when you ask it a question, the answer was derived only from information that you could have gone and derived it yourself had you been smart enough and enough time to go figure it all out. And so we've had this tool called Goofy, Grand Unified File Indexer, for a long time because we have this trillion files and people want to find their stuff and they want to find it fast and we have to obey POSIX because of need to know and all this kind of stuff. So it's a really cool tool. It's been in the open source for a long time. Won an R&D 100 award. It's really neat. Scales well, really screaming fast, and honors POSIX. But its job in life is to make your view of the POSIX file system look like an SQL table. And you can query it, and you can say, of the stuff that I can see, I'm only interested in stuff older than this and bigger than that and whatever. And before you pick your coffee cup up, even if you have a billion files, you have the answer. That's its purpose. But that's neat because it's making a view of the file system for you. Only you can see those things. And so we did a little demonstration a few days ago, actually, that if you convert those text, those PDFs, all those PDFs, if you convert them into vectors, and you store them in files, databases, that have the same permissions as the file, and you index them with Goofy, now you can do a query and say, I'm interested in all the vectors associated with all the files that I can see that are similar to these other vectors, and things like that. And so you can actually go do, essentially, AI, good old Pythagorean, and figuring out the differences between how long vectors are. That's what it does. And it uses standard off-the-shelf database technology, and it's simple and it scales. And so what this is this enables you to train a model on the common stuff and let everybody have their own view of what the answer they get using augmentation databases, RAGs, or whatever method you choose to use. And it all follows the POSIX file system. And if you index things as they change, as permissions change, they no longer will get the same answer anymore because it's not available to them. And so that's pretty cool. That bridges the gap between the object people who gave up and said, we just give up. This shit is too hard. We're just going to make it dumb. And us who bought into it, 70 years ago, and we have this huge legacy, and we've got to figure out how do we take advantage of these tools, but in our world of massive POSIX things and people having taken their Windows trees and their Mac trees, and they've moved them up, and want to index all that kind of stuff. It's in trees. It's in POSIX. If you don't have a way to do this, you're probably missing out. So anyway, that's interesting. And then my last one, my last one is PNFS. So I'm kind of partial to PNFS, probably because I helped start it like in 2002 at University of Michigan, long time ago. And why do I think it's cool? Well, I think these new file systems are cool in that they're new file systems, and the thing that I don't like about them is they're proprietary, and the other thing I don't like about them is they've all picked something of this big, huge graph of things that you could be good at. They've picked some subset. And that's all neat if you're going to have a file system this flavor for this application or thing, and this kind of file system for that thing, which is the way we operate today. We have NFS for home, we have NFS for projects, but we have Lustre for checkpoint. And if we want to do training, we probably have Avast or something else. Well, doesn't that suck? Wouldn't it be nice if there was an open source variant of this that worked on all those workloads? And even better, wouldn't it be cool if it shipped on a damn Linux CD? Oh, I'd love that, right? That would be great. If it was in the damn kernel that I installed on the compute node, and I didn't have to mess around with 5 different kernels, and then you start getting different versions of things, it's hell. It's the road to hell. And so that's why I'm excited about it, is we're not there yet, but we're getting closer and closer to getting there. And this is all of those things that one would want to have it do. And yes, it's got some deficiencies. One is it won't do n writers into one file. So I'm paying a developer to work at Hammerspace to fix that. It also won't do client parity, which Lustre won't do client parity. Vast won't do client parity, but everybody wants client parity because they don't want to do failover pairs and all the junk you got to do if you don't have client parity. We're putting parity in the NFS client. You're going to be able to buy a CD a year from now, and it will have client parity in it. Pretty cool. We're funding that too. What's it missing? It's missing an open Linux distro metadata server. Today, the only decent metadata server for PNFS is Hammerspace. Love those guys. We've been working with Tron Megalboost forever. He's the NFS kernel maintainer. But he himself would say, we need an open source version of all this stuff so that there can be a community around it. And so we haven't done anything about that, but I'm forming a set of companies that are interested in pushing that concept and building a Linux metadata server. And my idea is I'll take a little shim, I'll develop a little shim that does the protocol, and it's got some back ends so that you can plug in whatever kind of storage you want, and whatever kind of metadata server you want, and whatever kind of policy engine you want. And so I'm not going to write a whole open source metadata server. I'm just going to write an enabler, make it available, and then let people fight over it, which we think is a good idea. And then it also has some single directory scaling issues. Single directory scaling issues hasn't been solved yet. We did 3 tries on Lustre. We got DNE 0, which never was released. DNE 1 was released, and it didn't scale single directories, and DNE 2, which will scale single directories, just badly. Probably the state of the art in this space is Deos. Deos was designed kind of around this concept because several of us that did Lustre were thinking, God, if we could just solve this last problem, it would be great. It doesn't do a lot of other things all that well, but it does that really well. And so we're thinking about potentially marrying Deos with PNFS metadata server to fix all these problems at once. I'm not saying we're going to do that, but we're headed in that direction. We're also funding at CMU a PNFS test and evaluation center so that we have a few thousand node cluster and a bunch of data storage servers and a bunch of eager people that want to break things, and we're going to just break the hell out of it for a while until it gets good enough for us all to use, shipped on your Linux CD, we hope. I think I'll move on. So my message is we need to work together on tools to get us to that new place that we all don't want to go. And I have this thing called the Efficient Mission-Centric Computing Consortium, and that's a harpy, which is a bird that can kill a deer with its talons. And anyway, and the whole idea behind this is it's a mechanism for us all to collaborate with one another, technology providers and technology users, towards getting us to this next thing that we've got to become, because we have to morph into whatever our next life is. And that's all. Thank you.
Thank you, Gary. Does anybody have any questions?
Thanks, Gary. Great talk, despite the mention of CDs. And you may have a trademark problem on your last slide, but back to the sparse memory thing, which is definitely fascinating. Can you talk a little more about how the hardware support works for that, and whether it's on the processor memory controller side or on the DIMM side? Because if you have a sparse data structure, you still have pointers you have to chase eventually, right? And you still have to get to each memory location, which is non-sequential in the DIMMs unless you do something smart to store them that way. So how do you sort of avoid the cache poisoning that comes with going through the indirections?
Okay, that's a super good question. So the normal way is that you're in a loop, and you're multiplying 2 numbers together, and they're floating point numbers, and each number, you don't have the actual floating point number. All you have is a pointer to it, or you have a pointer to it, or something like that. And so the first thing you do is you unroll the loop, and you have all the indices. You must have, or you couldn't find them at all, and they're probably serial. And so you go through a serial thing, and you go through the loop, and you unroll the loop, and you make a indirect or doubly indirect or doubly indirect gather engine, a gather list, a vector with a bunch of pointers in it. You take that pointer and you call eventually through some compiler this thing called an indirect gather, which didn't exist until a few years ago and still doesn't do anything. And that will go to the processor's memory controller. And today, the processor's memory controller will just go do it serially, which will pollute the hell out of your cache because it'll go do this one at a time, and you'll send this out there, and then you'll send back the next indice, and you'll do this 3 or 4 times, and finally you got your one damn floating point number, and then you got to go do that again and again and again, and finally you can do your formula. That's the way it works today. We would ship that array all the way out to the controller underneath the HBM stack. And of course, you're going to talk to me about virtual versus real addresses, and yes, you have to deal with all that. But we've prototyped that, and so that array goes out there once, and it's a set of things to look up. That memory controller that's sitting out underneath the HBM stack has a map of a piece of SRAM back on the processor, in the memory controller part of the processor, and it takes and parallelizes that list. It also sorts it because you want to do it in page order and all the tricks we've played with this stuff forever. It takes that stuff, sorts it, redoes it, goes and does the lookups in parallel because every one of the banks has a bank processor. So each one is doing lookups. It populates that SRAM with the answers, hands the address of that SRAM that it made up back to the memory controller on the processor, and the processor hands you back this dense array, which is pretty cool. Then you can do vectors, data parallel units, whatever you want. So that's the idea, and we've actually prototyped this with one core, one socket being the memory controller for the other socket. And so we had a whole socket and all the cores on it trying to feed a couple of vector units on the other one to figure out the amdahlness of all this. Then we took that processor and we said, let's not have that be a processor, let's have that be an FPGA with some HBM on it. And so SK Hynix built us that. They put the microcode down in their little memory controller that's underneath the HBM stack, and we prototyped it that way, and we're getting huge speed ups, and if you sort it, you get even bigger speed ups. And we're still nowhere close to what you could do with real hardware. So that's how it works. But yes, there's an awful lot of arm waving there. I mean, some compilers got to unroll things. There's a lot of stuff to make it happen, which is why we've been working on it for so damn long. It's just hard. It's a great question. No, but I'm not sure I could do a Python variant of it.